Welcome back to our video module on quantum mechanics. We've spent quite a bit of time exploring potential profiles of various shapes, and today we'd like to continue on that path. Today's shape, and what I'm drawing here, is the finite square well, where we have a finite difference in potential energy within the well, and the well has an actual width. And today's question is, how do waves act in this potential profile? What does the wave equation look like? What type of energy states can we expect to see? Today, we'll be looking at the finite square well, learn to understand its basic behavior, and get to the point where we can start to address the mathematics behind it. Well, based on the work we've done thus far, how can we start to understand this? Well, it looks a little bit like the infinite square well, where we have discrete energy states, at least in here. It also looks a little bit like what we saw in the delta function, where we have an energy that is below the surrounding energy, but within a small location, the energy peaks out above the potential. Finally, we have this idea that the energy and the potential at some point are equal and they cross, just to this a little bit to the right, it's one way, a little bit to the left, it's the other way. Very similar to what we saw in the simple harmonic oscillator at the classical turning points. And to identify the form of the wave equation, we'll take the same basic approach where we'll look at, say, region 1, region 2, where E is less than V, and region 3 separately where E is greater than V. Let's clean that up and write down Schrodinger's equation and get started. And similar to the approach that we've taken previously, we'll split it up into regions. Region 1 and 2 is where x is greater than the absolute value of a. Region 3 is where x is less than the absolute value of a. Using the same approach that we've used before, we know in region 1 and 2, e is less than v, in this case v is 0, which means the second derivative of the wave equation with respect to x is k squared psi, where k equals square root of negative 2me over h bar. Solutions for these are real exponentials, which means we can expect wave equation as a function of x to be something of the form a e to the negative kx, where we're looking at something that exponentially decreases as we move away from the origin to keep the wave equation from blowing up. Likewise, for region 3, we can say that E is greater than negative V naught, and this is the same type of solution we saw when we were looking at the delta well with an energy that was below the surrounding potential. With that basic information, we know that we'll have a minus k squared psi, which equals a second derivative of psi, and we know that solutions for equations looking like this have a complex exponential. We saw this when we were looking at the infinite square well, which led to sinusoidal behavior. So we know that psi of x for region 3 looks something like an a sine to the kx plus b cosine kx. So let's erase and move things around a little bit so that we can try and figure out what this wave function might look like. Well, we know that within the region, we're going to have our sine and cosine, so it's going to look very similar to what we saw in the infinite square well. We know that in regions 1 and 2, where the energy is less than the potential, we're going to have a negative exponential, very similar to what we saw right here. So if I wanted to just guess it, I might make a cosine here, and then, I don't know, in a different color, we'll say yellow, make some sort of decaying exponential here. Or maybe let's do a first excited state with our decaying exponentials, and of course I've made this a little bit off, looking something like that. And in fact, this is what the wave functions of the finite square well look like. Where it gets really tricky is on the infinite square well, we knew what happened when we went outside of the well. The potential energy was infinite, so we knew that the wave equation there, the solutions were all zero. So finding boundary conditions here was relatively straightforward. However, here, the next step we need to take to solve this mathematically is to identify these boundary conditions so that these two equations can come together and be continuous. This is some fairly heavy lifting mathematically involving transcendental functions. So as you continue on this topic, you'll need to bring your A game. Finally, because these solutions in region 3 are sinusoidal, boundary conditions will be discrete, leading to an energy that depends on nodes, which is not altogether different than what we saw with the infinite square well. So in summary, by simply looking at the relationship between the potential energy and the energy of the wave, we're able to separate our potential profile into 3 basic regions. The behavior within those regions is very similar, if not identical, to many of the things we've already looked at. We can use the Schrodinger's equation in each of those situations to come up with a mathematical form, which gives us a good intuitive idea of what the wave equation solutions look like, how their energies act, and all that's left for us is to use the boundary conditions to identify exact solutions. Thank you for joining me for this quick intro on the finite square well, and good luck with your transcendental functions.